this chapter, we're going to start looking at applications of derivatives. In this lesson, we're going to spend some time looking at acceleration.
All right, hi everybody. So in this lesson, we're going to talk about acceleration. Actually, I'm going to get my little laser pointer going here. So now remember, in the previous lesson here, we looked at velocity, and velocity is the rate of change of displacement with respect to time, okay? And because displacement is a vector quantity, where positive means one thing, negative means another, we're going to have a similar sort of relationship with velocity, okay? So velocity becomes this vector quantity. Positive means going forward, negative means going backwards. So now we're going to just take this up a level, and we're going to talk about acceleration. And acceleration is the rate of change of velocity with respect to time. And again, because velocity is this vector quantity, acceleration is also going to be a vector quantity here. So there's going to be positive acceleration, negative acceleration. And so positive acceleration is going to be when velocity is increasing. Negative acceleration is going to be when the velocity is decreasing. Now you often hear people use the word decelerate. Actually, that's not really a word. It's not the best way to describe it. And you'll often hear physics teachers say, there's no such thing as deceleration. It's negative acceleration, right? And that's really what's going on here is that when acceleration is positive, this is increasing. When acceleration is negative, this is decreasing. Now, because it's the rate of change of velocity with respect to time, that makes it the second derivative of displacement with respect to time. So a little bit of notation here. So acceleration is going to be the derivative of velocity. And sometimes we use that dot there. Remember, the dot means a derivative with respect to time. Or it's going to be the second derivative of displacement. So two dots right here. Now, that's great and all, but you really don't get a nice sense of what's going on here until you look at the derivative in Leibniz notation here. So acceleration is the derivative of velocity, which is the second derivative of displacement. But look at how this is written. Notice it's d squared over dt squared. So notice what's not written here. It's not ds with the square outside. Now, the reason why that's not true is if it was ds squared over dt squared, really what that would be is the velocity squared. Okay, it would be ds by dt would be within this square here. That's not what it's saying. What's happening here is the derivative with respect to time. Okay, if you just look at what I'm circling here, the derivative with respect to time, that little bit there is an operator that acts on a function. So the derivative is an operator that acts on a function. We are taking the derivative with respect to time, okay, derivative with respect to time of velocity. Okay, so if you were to do this twice, okay, and actually maybe what I should do here is pull up a little note here, see if I can make this thing work the way I want it to do. So really what we've got going on here is if you're taking the derivative of displacement to get velocity, and I'm hoping this pops up right away here so I can show you. And here we go. So you've got your displacement right here. I'm not entirely sure why there we go. You've got our displacement right here. And then what we do here, oh, wow, okay, wow. You've got your displacement right here. Then we take the derivative of displacement, okay? And what we're going to do now, and this is velocity here, okay? What we're going to do now is we're going to take the derivative with respect to time of the derivative of displacement with respect to time. I think this is where it gets more clear. This little bit right here is that operator, that differential operator here, or the derivative here, that acts on this right here. Okay, so the derivative happens, this d by dt happens twice on displacement. So we get now d squared s dt squared. Okay, that's really how you want to understand that. And I think the notation here is brilliant, because when you take a look at the physics behind this, notice that the units for acceleration are meters per second squared, length per time squared. Well, the displacement isn't being squared here. Okay, and the units for displacement will be meters, kilometers, feet, inches, whatever units you're using here. But it's the time unit here that will be squared. Okay, so the notation here is consistent with the units that you would expect to get for acceleration. I think that's just absolutely brilliant that that all works together as nicely as it does. Anyway, sorry about getting all into that there, but let's take a look at an example where we talk about the different ways that we can use acceleration or find acceleration here. All right, so now here's our example, and you're going to notice that this is related to the example that we did in the lesson on velocity here. So for the position function, we're going back to s of t is going to equal t cubed minus 9t squared plus 24t, where t is in seconds and s is in meters. All right, so now we're going to answer some questions, but we're going to take a look more at the velocity end of the acceleration end of this. So to start off with A, when does the particle reach its maximum or minimum velocity? Okay, now let's think about what's going on here. When I talk about the maximum or minimum velocity, it's going to be very easy to fall into a trap of misunderstanding here and thinking that we need to do some work with the velocity function. But I want you to think about it. You're in a car, you're driving, you merge onto the highway. So you press on the gas. Now, as soon as you press on the gas, the car starts to accelerate forward, okay? You feel that push backwards, that inertial push backwards here. Once the car reaches its maximum velocity, okay, you're on the highway, let's say 110 kilometers an hour, that's when you pull off the gas, okay? Because you've reached the maximum velocity, you're no longer going to accelerate the car. Now, granted, because of friction resistance, you're going to have to put some gas in on, hit the pedal again to keep going here. But that first little instant where you pull off the accelerator, that's what we're talking about here. So when does the particle reach its maximum or minimum velocity? Now, in this case, we don't know, and we're going to figure that out in a second, whether it's max or minimum. But that's going to be when its acceleration is equal to 0. Okay? Soon as you stop accelerating, okay, then the velocity has stopped changing, which means we've either arrived at a maximum value for that for velocity or a minimum value for that velocity. Okay, I hope that makes sense. Usually we don't have too much of a problem with with the relationship between velocity and displacement. You know, you throw something in the air, it goes up, and it's got this positive velocity, but the velocity gets smaller and smaller. Hits 0 up here, so it stops moving, and that's the maximum displacement that you get to, and then it comes back down again. Very, very similar relationship here. So the first thing I'm going to do is I'm going to figure out what my displacement derivative is. That's going to be velocity, and that is going to be 3t squared minus 18t plus 24. Excellent. So that's not what I need. I need acceleration here. So take the derivative of velocity, that's going to get us acceleration, and that will be 6t squared minus 18. Okay, so now what I want to know is where does 6t squared, 6t minus 18. So now I want to know is where does 6t minus 18, where does that become 0? And that's actually really quite straightforward to solve. At the 3-second mark. Now, is the velocity a maximum or a minimum at that part here? Well, let's take a look at what's going on with this acceleration function right here. Okay, so if this is my coordinate plane here, if I was to graph acceleration as a function of time here, what I've got is a linear function with a positive slope, negative y-intercept here. So it's going to look something like this. Now, let's not argue about the slope of the whole thing here and what that's going to look like, but it's going to roughly look like a line that goes up like that. We just found that it's got an x-intercept here of 3, or a t-intercept, I should say, of 3. Now, to the left of this, okay, 3, in this region right here where t, and actually I should say it like this because to be honest it's not going to go beyond there. probably shouldn't have written it like that. It's only going to go up to the 0 there. From 0 out to 3, okay, my acceleration is negative. From 3 out to infinity, the acceleration is going to be positive. So what this means right here, when the acceleration is negative, bear in mind, again, what we're talking about here, this means that the velocity is getting smaller. Then we hit 0, and then from that point on, it starts to get larger again. So therefore, at t is equal to 3 seconds, the velocity is a minimum. Okay? Now I could have gotten that really by graphing the velocity as well. Okay? In fact, if I take a quick look at the velocity function over here, okay, and we looked at this last time here, velocity is equal to 3t squared minus 18t plus 24. If I factor that, okay, t squared minus 6t plus 8, and we get 3 t minus 2, t minus 4, whoops. We can see that the velocity goes to 0 at 2 and 4. It's a parabola that opens up, so it's going to look something like that. Okay, right, it doesn't go past there. But I can see that the velocity gets smaller, Here's 2, here's 4, and then right in between there at 3, it's going to hit its minimum. But I already determined that that was the case here by looking at the acceleration. Okay, neat. Back up here. What is the maximum or minimum velocity? Okay, now to figure that out, I actually do have to go through and use my velocity function right here. Okay, so my velocity, I now know that the time that I'm interested in is at is at 3. So I could plug that up into here and work that out. That would be quite easy. I think factored form is going to be a little bit easier. I'm actually glad I did that. So 3 minus 2, 3 minus 4. In fact, I'm super thrilled that I did factor it because it makes it so much easier. Because 3 minus 2 is 1, 3 minus 4 is negative 1, which means my velocity was negative 3 meters per second. Makes that really, really easy. These two questions usually will come in tandem. I'll ask you when this happens and then what was the value that you got. Okay, good. Now let's take a look at C. What is the average acceleration over the third second? Now, I believe in a previous lesson we have looked at or talked about questions similar to this, but it bears repetition here because after you get through the chapter on motion, it's very easy to get to the exam, and when you get asked a question about averages, to make a mistake and to flip into the wrong thing here. It would be very easy, for example, when I ask you for the average acceleration, to go up here to my displacement function, go, okay, he's asking for acceleration, I'm going to take the derivative twice, and I'm going to figure out what the acceleration is on either side of that third second and take it from there. But that's not the way this works. Okay, the average acceleration is going to be the change in velocity over the change in time. So important that you catch that. Whoops. That the average acceleration is the change in velocity over the change in time. Okay, let's zoom in a little bit here. So this is going to be equal to the velocity at, well, now that's interesting. Let's take a quick look at this. It says over the third second. Well, what times are those? Let's take a look at our number line here. Here's 0, 1, 2, 3, 4. From 0 to 1, this is our first second. This is our second, and I know it sounds goofy to say it, but it's our second second. This right here, this is our third second. Now notice that it ends at time equal to 3 and begins at time equal to 2. So if I want to figure out the average acceleration over that time period, I got to take that final velocity, subtract the initial velocity over the change in the times there. Okay, now I'm not putting absolute values on there either, okay, because I am curious about whether the acceleration is positive or negative. It is a vector quantity here. So what I'm going to do is I'm going to go to my calculator and I'm going to enter that in. Actually, you know what? I'm not going to do that. I've already got this worked out in factored form. It makes it easy for me to do this. Velocity at 3 seconds, okay, I already figured out was going to be -3. Minus, let's go back up here. Velocity, actually maybe I'll do is I'll come over here. The velocity at 2 seconds is going to be 3 times 2 minus 2, 2 minus 4. Okay, well, I don't know why I underlined that. was getting excited about doing the division over here. Well, because of this term right here, I know that that is actually going to equal 0. So this is going to be -3 minus 0, okay, over 3 minus 2. So the answer here is going to be -3 meters per second. So not only is the the velocity -3 meters per second, the acceleration, the average acceleration over that third second there is also -3 meters per second squared. Now, granted, the units are different, but the numeric value there is the same. Which is just a coincidence, by the way. Don't think that there's some sort of a rule developing there. That's just a coincidence in this particular problem. Okay, now, the last question that we're going to ask here is, when is the particle speeding up? Okay, that requires a little bit of a lead-in explanation to talk about that. So here's D here. Let's draw, here's the origin. Let's draw this out. When we talk about speeding up, okay, it's not just a matter of velocity being positive or acceleration being positive, okay? Because there's two different scenarios here where you could be speeding up, okay? Let's say, for example, here's your origin. Let's say that you're right here and you have got positive velocity. Okay, so you're moving to the right here. Now, well, think about it like this. Actually, this might be an even clearer way of doing it. Do you know those horizontal bungee things that you can rent where you get, like, you've got this huge bubbly thing here and there's a bubble wall here with a strap, and then it comes out and here you are, you're in here and you're running and you're strapped in, okay? So you are running this way, but as you're running across here, you're getting pulled back, and the further you go, the more you get pulled back. So what's happening here is you've got forward velocity, but your acceleration is this way. What happens to your speed? Well, your speed slows down, okay? So if you've got something like this where your velocity is positive, but your acceleration is negative, okay, this is when you are slowing down. However, let's say all of a sudden, okay, you stop running, and all of a sudden, oh, that looks like it's grabbed around your neck. But anyway, here we go. Woo! You've stopped running, and all of a sudden it starts yanking you back. Now all of a sudden, your velocity is this way, the force is this way, so the velocity is negative, your acceleration is negative, it's towards the left there. This is when you start to speed up, okay? Because now you're moving this way, you're moving with the force, not against the force. And when that happens, you start speeding up. Now, that can happen in two different ways here. So in this case here, I'm slowing down. But let's say I had velocity going forward, so velocity is positive, and acceleration is positive, if they're both in that direction. So this is like me getting out into the highway, I'm moving forward, I hit the accelerator, I'm speeding up, my velocity is increasing forward. That's going to be speeding up. Or my velocity could be negative. So if my velocity is in this direction, in order to be speeding up, my acceleration also should be in that direction. Now think of it like this. Another way to explain this maybe is if I throw something in the air, initially its velocity is positive, its acceleration is negative. That's why it slows down until it reaches the peak of its trajectory here. When it starts to come back down, its velocity is negative, its acceleration is also negative. So it's moving with the force of gravity, and that's when it starts to speed up. So in either of these situations here, we're going to get a situation where the particle is speeding up. Now notice, either they're both positive or they're both negative. Now multiplying velocity by acceleration Doesn't mean anything physically, but it does give us a little mathematical trick, okay, for determining when they're both in the same direction. Because if their product is positive, they're both in the same direction, and that is going to mean speeding up. And no, by the way, on the other hand here, if we're asking where it's slowing down, okay, so this right here is going to be speeding up. On the other hand, if velocity times acceleration at some point or some time is negative, then it's slowing down. So, in this question, we are interested in where velocity times acceleration is greater than 0. We already know, okay, that velocity is going to be 3t squared minus 18t plus 24. And we know that acceleration is going to be 6t minus 18. We're interested in where that product is greater than 0. Now, don't expand that out. You're going to make it harder to work with if you expand it out. You want to factor it, because what you want to know is what this graph looks like. We're going to take this problem, this question about the value of this product, and we're going to convert it into a graph so that I can see the answer. Makes it so much easier if you can see it. But to do that, I need to factor. Now, we've already factored the velocity function. We did it on the last lesson here. I can take out this 6 and make this t minus 3. All right, so this particular function, which by the way happens to be cubic because it's a quadratic multiplied by a linear, has got 3 roots, t equals 2, 3, and 4. Okay, when I multiply 3t squared by 6t, I'm going to get 18t cubed, so it's a positive cubic. So we've got 2, 3, 4. Positive cubic is going to be moving up. The multiplicities of all those roots are 1, so it's going to go through, go through, go through. And somewhere over here is the 0. That's going to be our boundary point. Stops right there. So where is this graph positive? Well, it's positive between 2 and 3, and where the function is greater than 4. Okay? Or if we want to use interval notation, this is speeding up between 2 and 3 and from 4 out to infinity. Okay, those are the time intervals over which this thing is speeding up. Now, I hope you see the connection between what we just did here and what we were doing with velocity and how velocity relates to displacement. Very, very similar sort of a thing. Very similar sort of a relationship, I should say.